I made a couple visualizations I wanted to share with you guys. I think these will help address some of my most frequently asked questions. Basically, there are just a handful of different categories you can throw every comment that I've received into. Like there's these different buckets. You have one bucket of just lunatics that just say a bunch of nonsense that you can't understand. That's a good 10% of comments. Sometimes I'll just delete some of those because they literally do not make sense. It's like crazy people. I've stopped deleting comments though because I pretty much am just going to ignore comments. My hope was to get a sort of peer review, but YouTube commenters are wow, they're a little wacky. But then you have some praise and supportive comments. Those are the best. Those keep you going. That sort of thing really, really helps. It's like just saying, hey, I enjoyed the video, or this is intriguing to think about, or thanks, or if you don't like it, then just move on. That's fine too, because I would not like my videos. Of course, I probably would. I watch a lot of weird stuff on YouTube. Like YouTube, to me, like YouTube's amazing because it's a bunch of non-mainstream stuff. I don't like the polished, super edited things. I like authenticity, and there's a lot of that on YouTube. Of course, it's drifted away from that. There's a lot of that has to do with technology, though. There's a lot of options for video editing these days, and so that helps out. But I'm not good at that sort of thing. I would rather spend my time doing other stuff. But I did manage to create a couple of visualizations to address the other types of comments because, like I said, there's these multiple buckets. There's praise, and then there's loonies, and then there's people that disagree with me and they have their own ideas. Well, whatever. That seems to be like that's a good 50%. Like it's a large portion. People don't really like to hear what other people think. I don't know why they watch other videos. I don't watch other cosmology videos. Like that's definitely not something. Like I'll watch some math videos or something like that, but or maybe something on general relativity. I'll watch a lecture by Leonard Susskind or something like that. But I usually don't want to watch like finding clips to play in my videos. Like for my top 10 video, I had to find a video. I wanted to find a clip of Sean Carroll saying something outrageous. And to do that, I had to list it, and it just gives me severe anxiety. It's like so cringe to listen to them describe the universe, the early stages of the universe, and all this stuff. It's so hilarious. But I did come up with a couple visualizations to describe the metric that I'm proposing. The other comments that are legit, the ones that are legit, they have a difficult time understanding why there's not a corresponding blue shift, because this is the mainstream cosmological view. They think that if the universe is homogeneous, then there's going to be a corresponding blue shift that cancels out the red shift. And so this visualization will hopefully clear that up with the metric that I'm proposing. You have two options for red shift or blue shift. And now this is on the cosmological scale, okay? Because symmetrically speaking, it reduces to the Schwarzschild metric. But symmetry is required. So you have to be on a larger scale, like the clumpy parts of the universe, like around the local galaxies, like less than a megaparsec or so. The local effects are going to be much more dramatic than the cosmological effects. And so the metric solution won't apply to the smaller scales. But the larger the scale you get, the more symmetry you have, and the more relevant this metric becomes. So in this image, you have the blue dot. That's Earth. It's in the very center. For this metric, for a star, now it does look like this star is very close because, like, I can only do so much with of this visualization. It's as simple as I could make it, and it was still really complicated. But you have a star, that's the white circle, and then you have Earth, it's in the middle. With this metric, it's all going to reduce to either gravitational redshift or blue shift. So on the left side, there's an object that's emitting nothing, or it's emitting light, but it has no mass. That's what I meant to say. So it's a massless object surrounded by nothing, and it's emitting light, and you're observing it from this blue dot in the center. The white circle is a star emitting light, and they're the exact distance apart. They're always going to be the exact distance apart. As we increase the radius, what I call the sphere of influence, the amount of mass that is contained increases when the radius is longer. So the further away that the star is, the more mass there is to cause a redshift. If the light was emitted from a location with zero gravity, or no gravitational well, then there would be a corresponding blue shift that would be of this. However, that would probably not be visible light, because anything that has no gravitational well is not going to produce enough light. Now, it does come into play when I'm predicting the cosmological background radiation, the CMBR. We're going to get to that in just a second. I hope everybody understands. I have the radius for the slider, and it's in megaparsecs. And this is the density. This is according to something like a Hubble's law, 72 kilometers per second per megaparsec. If this is your first time, I should probably tell you, if this is your first time joining me, if you've not watched any of my other videos, it's important to know that I am proposing a metric solution that uses a mass density that is inversely proportional to the radius. Now, I discovered this because I built this metric from the Hubble redshift. It's what you do. Step one is you assume that it's not expanding, the universe is not expanding, that the cosmological redshift is caused by gravitational redshift. Then you work backwards from that and you find the mass density distribution. Then you formulate a metric solution for that. Fortunately, this was super simple because it's just straight up defined by a minimum gravitational acceleration, which equates to an inverse mass density, or a uniform gravitational acceleration. I can show you the metric solution. Most of you have no idea what I'm talking about, but it may be relevant for some people, especially my audience, may be pretty smart. So, God, I hope these are accurate. I haven't looked through this in a long time. I'm trying to replace my existing article. I'm trying to hurry up and finish it, but there's only so much time in a day. I got to work too. So this is the interior solution to the Schwarzschild metric. This is the solution I'm proposing. This is the solution that contains the density distribution, the required density distribution to produce the gravitational redshift that I'm discussing. Okay, this is the Schwarzschild metric. It is a subset. It is the Schwarzschild metric. This is the interior solution of this Schwarzschild metric. It has continuity with the exterior solution. The only thing that I'm saying is that the mass density is inversely proportional to R. So this is how Einstein is able, or this was what Einstein was looking for. Einstein was wanting to find a stable distribution. He did not think about this. No one thought about this. Apparently no one has published this. To me, this is super simple and super obvious. Regardless, let's go to the next one. So as the radius of this increases, let me go to this. So let's just move this star all the way to 4,100 megaparsecs or so. This is the total mass that you have in this region, okay? If you use this along with the Schwarzschild radius equation, then you find out that the observable universe is a black hole. And so that's what this visual is for. So with this visual, excuse me. How long are we in? 10 minutes and I've already got dry mouth. Making YouTube videos is difficult, man. Anyways, Schwarzschild radius. So both of these balls represent different objects. Well, man, I am messing that up. I'll probably cut this out. Let's go Schwarzschild radius. The object on the left is just a hypothetical object. Okay? It's a hypothetical object with this radius and this mass. So you can adjust the slider to adjust the size of the hypothetical object. Okay? The hypothetical object, the object on the right is the Schwarzschild radius of the hypothetical object. So if this hypothetical object with a radius of 817 megaparsecs and a mass of 3 times 10 to the 51 kilograms, it would have a Schwarzschild radius of 1.6 times 10 to the 2 megaparsecs, whatever that is. 1600 megaparsecs. Which that don't sound right, but that is right. I guess that is right. 870 megaparsecs is a huge distance. So if we increase this object, this is its Schwarzschild radius. But if you notice, the Schwarzschild radius is smaller because this is a black hole. But mathematically speaking, as you keep increasing the radius, we're now at 4,000 megaparsecs. Look, the Schwarzschild radius is getting larger, more quickly. And then around the 4163, where is this at? It's supposed to be there we go. 4161 megaparsecs, they are the exact same size. And then from here on out, the Schwarzschild radius gets larger. That means that at 13 point whatever billion light years is the Schwarzschild radius of our universe. And that's you can use the critical density, published estimated critical densities, or estimates of the critical density. You know what I'm saying. And it's going to be 13 point whatever billion light years is the Schwarzschild radius of the observable of the universe. It's going to be approximately the same age of the universe. To me, that is remarkable. Okay, that is absolutely remarkable. Also, since it's not that the universe is a black hole. I mean, you can call it that because for an observer that is twice that distance from us, it would appear that way, But basically, there's no information that can be pulled from us if you are, what is that? 20-something, 26 billion light years away. Anyways, since we're dealing with a Schwarzschild radius, and since it's a black hole, like physically speaking, it doesn't have a singularity, but it has a Schwarzschild radius. We should be able to obtain Hawking radiation. And if you use this blue shift method that I was talking about earlier, where the Hawking radiation is being blue shifted, and you use the maximum amount of gravitational force possible, like all of the gravitational force in the universe at the furthest possible distance, the closest to the Schwarzschild radius that you can get, or maybe even beyond the Schwarzschild radius. Maybe, and that's what I can't decide. I can't decide if it's one Planck length beyond the observable radius, or if it's one Planck length before the observable radius. I actually don't know the answer to that. Where the particles would be created and generate the CMBR. But that would be like a Planck length is like your eyeballs are moving more than that at all times. So I don't really know if that makes a difference. It seems like that there should be another limitation. Like my interpretation of finding the maximum factor of change due to general relativity is not appropriate equation. There should be another limitation. I came up with 6 degrees Kelvin. So, But that 6 degrees Kelvin would be the maximum Hawking radiation that you could observe. Like, there's no other, like, that would be a black hole the size of the observable universe, blue shifted uh, all the way, you know. And so it's like, that's the maximum, like, that is, you can't get any more than that. And so I came up with 6 degrees Kelvin, so it's close to that. You know, I'm off by a factor of 2 or something. I'm not exactly sure. There's probably a better way to do it than I came up with. I was hoping somebody else would assist me with this, but most people just want to make negative comments and stick their tongue out and call me stupid. I'm like, okay, well, I don't know, but my metric solution's great, you know, and to me that eliminates inflation, that eliminates dark energy. There's a great potential to explain uh, dark matter with that if you use MOND, and basically this would be like the source of MOND. This metric solution would be the source of MOND because there is this uniform G or minimum G, depending on how you want to look at it. It's not uniform because you can obviously get higher than G, but on the largest scales, the symmetry says that it's just a uniform gravitational acceleration. So, anyways, I've rambled enough, but check out these simulations. I mean, I think that this helps. I don't know. These visualizations, I don't know. Do you think they help? I don't know. I don't even know why I'm doing this garbage. But somebody needs to think about this. I think. I don't know. Y'all have a great night.